Hello everyone. Since the previous week, we have been looking into seismic design and ductile detailing of reinforced concrete buildings. In the last class, we have discussed about seismic design of special shear walls, which are a type of lateral load resisting element used in reinforced concrete buildings. Today, we will see an example to illustrate the design of special shear walls. So, let us first look into the problem statement. We need to design a 5 meter long reinforced concrete special shear wall for a 4-story building with a story height of 3.5 meters, which means the height of the special shear wall will be 3.5 into 4, which is 14 meters. The length of the wall is 5 meters. The design loads obtained from linear structure analysis are as follows. This is usually obtained using commercial softwares. So, in this case, we have obtained the design axial force to be 2500 kilonewton, the design bending moment as 7500 kilonewton meter and design shear force as 500 kilonewton. We need to use concrete of M25 grade and the steel reinforcement of Fe 500 grade. So, we are aware of the material properties. We are also aware of the geometry of the special shear wall, except the thickness, which we shall assume. We are aware of the design loads. Typically, a special shear wall will resist through 3 actions: axial force, bending moment and shear force. So, all of the 3 are given over here. Let us try to solve the problem. So, the first step would be to arrive at a geometry. So, in this case, the length and height is known to us. We will assume the thickness of special shear wall. In this case, we have assumed it as 300 millimeters. You could have very well assumed it to be 200 millimeters. However, in case of coupled shear wall, we have seen about coupled shear wall where 2 shear walls are connected using a coupling beam. So, 2 shear walls being connected through a coupling beam. In that case, the coupled shear walls will have a minimum thickness of 300 millimeters. So, we have designed this shear wall such that we will have the scope of coupling the neighboring shear wall. Okay. So, let us assume the thickness to be 300 millimeters. Then what will be the length to thickness ratio? The length of the shear wall is 5 meters, that is 5000 mm divided by 300 mm, which turns out to be 16.67, which is greater than 4, and hence this structure or member falls in the category of special shear wall. If it were less than 4, we would have designed it as a column. Now, we will classify the shear wall based on the height to length ratio. In this case, the height is 14 meters and the length is 5 meters. So, the height to length ratio is 2.8 and it exceeds 2. That is why we classify it as slender shear wall. We are aware of the design forces and moments, which we have also given in the previous slide related to problem statement. Now, we will find out whether do we need boundary elements or not. So, for that we will calculate the stress at the extreme compression fiber. So, whenever there is a shear wall, if you apply a lateral load, on the one end there will be a compression and on the other end it will be a tension. So, we will try to find out what would be the stress at the extreme compression fiber. How we will calculate that? It will be calculated as P by A plus M by Z. We know that the factored or design axial force is 2500 kilonewton and the cross sectional area is 300 mm by 5000 mm plus the design bending moment is 7500 kilonewton meter and the value of Z is BD square by 6, which will be 300 multiplied with 5000 square divided by 6. So, upon calculating, we get the stress at the extreme compression fiber as 7.66 megapascal. Now, it exceeds the value of 0.2 FCK. The value of 0.2 FCK for M25 grade of concrete will be 0.2 into 25, which is 5 megapascal. So, since the stress at the extreme compression fiber is greater than 0.2 FCK, we will need to provide boundary elements. So, boundary elements shall be provided at the wall edges. Now, in this case, if you are providing boundary element, one thing is that you can provide boundary elements which have the thickness at least equal to the thickness of the wall. You can go for larger thickness, but since in this case we have already assumed the thickness of a special shear wall to be 300 mm, which is on the higher side. So, we have assumed that the boundary elements are flush with the wall, which means the dimension of the boundary element shall be 300 mm in the direction perpendicular to the wall plane. Now, when we are choosing the boundary element, we should make sure that the boundary elements do not have an aspect ratio of, let us say, 2:1. It should not be more than that. Up to 2:1 is alright. So, in that case, we will adopt the length of the boundary element to be 500 mm. So, the boundary elements will be 300 millimeters by 500 millimeters. Typically, this boundary element shall be located within the wall, which means out of the 5 meter length of the wall, 500 mm from the left end and 500 mm from the right end shall be termed as boundary element, and the reinforcement detailing will be different in the boundary element. We will look about the reinforcement detailing as we go through the today's class. So, the remaining wall web is now actually 300 mm by 4 meters. Alright, since the total wall length was 5 meters, now the wall web is actually 4 meters length. Then, since we have assumed the wall thickness to be 300 millimeters, which is more than 200 millimeters, we need to provide reinforcement in 2 curtains. One curtain will be closer to the surface in front of you and the other will be at the behind. So, closer to both the surfaces there will be a reinforcement mesh, that is 2 curtains overall, and each of those curtains will have vertical as well as horizontal reinforcement. Now, if your wall thickness was up to 200 millimeters, then we would have checked the stress, and if the stress was exceeding 0.25 times of square root of FCK, then in that case we would have needed to provide reinforcement in 2 curtains. We have looked about those guidelines in the previous class, probably in lecture 6.3 and 6.4. You can always go back and look into that. I also suggest that you need to have a copy of the code IS 13920 during these classes, so that you can make the most use of the class. Now, we need to provide the reinforcement in 2 curtains. Let us now get into the reinforcement detailing. So, first of all, we will look into the vertical reinforcement detailing. For the vertical reinforcement detailing, we will start by providing the minimum vertical reinforcement. Now, as per the table 1 of the code, we have the minimum reinforcement in various directions given in IS 13920. So, from there, for the wall web in the vertical direction, we have considered the minimum vertical reinforcement in the wall web to be 0.0025. Now, to recall, this rho is nothing but the area of reinforcement divided by the cross sectional area. In this case, since we are considering vertical bars, the cross sectional area will be 300 millimeters times of 4 meters, the wall thickness multiplied with the wall length. Okay, since we have classified the wall to be slender, we will use appropriate expression. So, from that expression we have got 0.02025. Now, in this case we will assume 10 millimeter dia vertical bars in 2 curtains, and when we find this out, we get SV to be 209.43 millimeters, which means that these 10 mm dia bars in 2 curtains need to be provided at a spacing which is not larger than 209.4 millimeters. So, we will be providing 10 mm dia vertical bars at 200 millimeters center to center spacing in each curtain. Now, if we were providing in only one curtain, then this 2 would have been dropped. So, in that case you would have got the value of SV which would have been half of this. So, now we have already provided the vertical reinforcement detailing. Let us try to find out how much we have provided. So, we will calculate the value of P, and this we have found out to be 0.26%. So, basically what it means that we needed 0.25% and we have provided 0.26%. Now, let us check the vertical reinforcement whether it satisfies the ductile detailing requirements or not. So, the first ductile detailing requirement suggests that the largest diameter of vertical bars shall be less than 1/10 of the thickness of the shear wall. In this case, the thickness of shear wall is 300 millimeters, and that is why the largest diameter of vertical bars can be 300 by 10, that is 30 millimeters. In this case, we have used 10 mm dia bars, so it is perfectly fine. The second guideline related to ductile detailing is about the spacing of vertical bars, which says that the spacing cannot be more than any of these. The first criteria is 1/5 of the horizontal length of the wall. So, the horizontal length of the wall is now 4 meters because we have 500 mm long boundary elements on either end. So, the wall is actually 4 meters long now. So, the 1/5 of the horizontal length of the wall is 4000 divided by 5, which means 800 millimeters, and 3 times the thickness of the wall web. So, the web of the wall is 300 mm thick, and that is why we have to provide a spacing which is not more than 900 millimeters. And the third criteria is directly 450 millimeters, which means that out of these three, the lowest being 800 millimeters, we need to provide these bars at a spacing not exceeding 800 millimeters. But since we have already provided at 200 millimeter, now out of these criteria we will select the criteria which is most stringent, that is the spacing of vertical bars cannot exceed 450 millimeters, which is the lowest of these three. Since we have already provided the spacing as 200 millimeters, which is already less than 450 millimeters, so this satisfies the ductile detailing requirement and hence is acceptable. Now we will go to design or detail the horizontal reinforcement. At this point, we have learnt it from the column, so it will be much easier. So, the nominal shear stress will be calculated by dividing the factored or the design shear force by the shear area. What is shear area? It is the thickness of wall multiplied by effective depth of the wall. Effective depth of the wall is considered as 0.8 times of the length of the wall. So, we will have tau V as 500 kilonewton divided by 300 mm multiplied with 0.8 multiplied with 4000 mm. So, we get tau V as 0.521 megapascal. Now, the design strength of concrete estimated from table number 19 and clause 40.2.2 of IS 456, the value of tau C is 0.365 megapascal. Further, based on table 20 of IS 456 2000, the value of maximum shear stress tau C max is found to be 3.1 megapascal. Now, the value of nominal shear stress, that is 0.521 megapascal, lies between tau C and tau C max. What does it imply? It implies that the concrete itself is unable to carry this nominal shear stress. However, the section is suitable and the section can carry the remaining shear stress, and the section can carry the nominal shear stress, but you need to design shear reinforcement for the balance shear. So, that is why we have now designed the transverse reinforcement, AH being equal to VU minus tau C TW dW. Here VU is the design shear force for which we need to design the section, and tau C TW dW represents the shear force that can be registered by the concrete in the shear wall divided by 0.87 F by D by SV. Once we substitute various values, we get, upon assuming that we will be using 10 mm dia bars in each curtain, we have calculated the value of AH, and on substituting all these values from this expression, we shall be able to find the value of SV to be 1460 millimeters. So, the horizontal reinforcement of 10 mm dia in each curtain shall be provided at a spacing which is not exceeding 1460 millimeters. For this, if you calculate the value of rho h, that is the total steel area divided by the cross sectional area, in this case since we are dealing with horizontal reinforcement, the cross sectional area shall be from the side, that is thickness of the wall multiplied with the height of the wall. So, this value of rho h comes to be 0.0004, and if you obtain the value of rho h minimum, the minimum steel that you can provide based on table 1 of IS 13920, then the value of rho h minimum comes to be 0.0026, which is much higher than this value of rho h required, that was 0.0004. So, we need to provide at least the value of rho h being equal to 0.0026. This is very similar to the vertical case, right, where we had to provide minimum of 0.0025, but we ended up providing 0.0026. So, in this case, we will again provide 10 mm dia vertical bars in two curtains at a spacing of 200 mm center to center in each curtain. If you check this, it shall be suitable, because I have checked it here, the value of SV was coming to be 201 millimeters. So, we are providing 200 millimeters in this case. Now, let us check whether this horizontal reinforcement is satisfying the ductile detailing requirements or not. So, again we have the similar three criteria which were also true for vertical bars, which is 1/5 of the horizontal length of the wall, which is coming to be 1000 mm, 3 times the thickness of the wave of the wall, which is now coming to 900 millimeters, and 450 millimeters. So, we need to provide the horizontal reinforcement at a spacing not exceeding any of these, which means 450 millimeters. We have provided the spacing as 200 millimeters, which is less than 450 millimeters, and hence it is okay or appropriate. Now, once we have obtained the reinforcement detailing in the vertical and horizontal directions, it is time that we also run a check or design the shear wall for axial force and bending moment. So, under the action of axial force and bending moment, the special shear walls can fail in two modes. One of them is flexural tension failure and another is flexural compression failure. We all know that flexural tension failure is far more ductile mode of failure than flexural compression failure. In case of flexural tension failure, the steel on the tension side of the wall fails much before the concrete on the extreme compression fiber fails by crushing. So, here the depth of the neutral axis will be lower than the limiting neutral axis depth. So, therefore, expressing it in terms of a ratio to the length of the wall XU by LW, we have assumed it to be less than XU limiting upon LW. The expression is provided in annexure A of IS 13920. Based on that, we have calculated these values, and upon checking we have found out that this assumption is correct. I am not going into much detail of this calculation because the expressions are already available in the annexure A of IS 13920. I would recommend that you may pause the video and have a look into these. Okay, once we have justified that our assumption is correct, we will calculate the moment of resistance. So, the moment of resistance is calculated using this expression, which is again available in annexure A of IS 13920, which requires us to calculate some constants, and after substituting those constants we get the value of mu, and this is the moment of resistance or the ultimate moment carrying capacity of the RC shear wall. Here we have obtained mu as 5608 kilonewton meter. So this is the ultimate moment carrying capacity of the special shear wall we were designing. However, it is less than the design moment. What was the design moment? We were having the design moment of 7500 kilonewton meter. So it is lesser than that, which means that the designed wall will not be able to carry the design bending moment, and therefore we imply that the remaining bending moment shall be registered by the boundary elements. Remember that this calculation is only for the wall web, which means the length of 4 meter. Boundary elements on either side, that is 300 by 500 millimeters, that has not yet been accounted. So what we believe that the remaining roughly 2000 or 1900 kilonewton meter of moment shall be registered by those boundary elements, but we need to design those boundary elements. We have earlier established that in this case, since our extreme compression fiber was having axial stress of more than 0.2 FCK, we actually need boundary element, and in this case we also need boundary elements from the design perspective as well. So let us look into the design of boundary elements. So if we carefully look, out of the 5 meter length, 4 meter is covered by the wall. So each of the boundary element being 500 mm long covers a fraction of 0.1 of the area covered by the wall. This is calculated as 500 divided by 5000. So it is 0.1. Now in this case, since we have the lateral loading, one of the boundary elements will act as a compression element and the another will act as a tension element. So we will check each of them. So for the compression element, what is the total compressive force, that we need to find out. What will be the factored gravity load? It will be 0.1 times of 2500, that is 250 kilonewton. How did we calculate? Since the design axial force was 2500 kilonewton and this boundary element is covering 10% of the wall, so the factored gravity load carried by the boundary element will also be 10% of the total factored axial force. So it is 250 kilonewton. Now due to the external moment, there will be compression in this compression element. How much compression? So the remaining moment, which is 7500 minus 5608 kilonewton meter, has to be carried by this wall. So the lever arm becomes 5000 minus 2 into 250. Why? 5000 is the total length of the wall, and these two boundary elements have their CG located 250 millimeters inside from either side. So the lever arm between this compression member or the compression boundary element and tension boundary element, how much will be the lever arm? 5000 minus 2 into 250, which comes to be, upon calculation, 420 kilonewton. So the total force in the compression element becomes 250 plus 420, 250 kilonewton from the gravity load and 420 kilonewton from the external moment. So the total becomes 670.4 kilonewton. Now let us calculate the axial load carrying capacity of this compression element. Now since the compression element has the shear wall connected throughout, the compression element will be considered as a short column without any classification. So this is the expression for axial load carrying capacity of short column: 0.4 FCK AC plus 0.67 FCK PU equals 0.4 FCK AC plus 0.67 FYASC. So in this we have contribution coming from concrete, which has a area of AC. Please make sure that this AC area of concrete is gross cross sectional area minus the area of steel. You can think of not removing the steel area for an easy calculation, but that will be slightly non-conservative. So it is better that you remove that steel area, and this contribution is from the steel reinforcement bars. So if we substitute these values, then we get the value of axial load carrying capacity of the compression element as 1890 kilonewton. Now here I would like to point out that we have assumed the value of ASC to be 1200 mm square. What is the basis? Because in a column the minimum steel that you can provide is 0.8%, and this boundary element behaves like a short column. So you need to provide minimum 0.8% of steel, which accounts to 1200 millimeter square of steel area. So that's why we have substituted 1200 in case of ASC, and in case of AC we have calculated the gross cross sectional area minus 1200. I hope this is clear to you, and once we have found out the axial load carrying capacity, this capacity is more than the total force in compression. So which means our section is suitable and safe. Now we also need to satisfy some ductile detailing requirements. What are the ductile detailing requirements? Now we need to provide steel. How much steel shall we provide? Since we need at least 1200 millimeter square of steel, if we try to calculate, we can provide 6 numbers of 16 mm dia bars, 3 on each face. The provided steel shall be 1206 millimeter square, which is very marginally above the required steel. You could have provided maybe 6 numbers of 20 mm dia bars or 8 numbers of 16 mm bars. You could have provided. I have made it very economical, so I have just provided 6 numbers of 16 mm dia bars. Now let us check whether this provided steel satisfies our ductile detailing requirements or not. So the maximum diameter of vertical bars should be 1/10 of the wall thickness. So the wall thickness is 300 millimeters. So the maximum, so you can use bars which have diameter up to 30 millimeter. Since we are using 16 mm dia bars, it is completely alright. Further, if the boundary element was not to be provided, then in that case also you should have at least provided 4 numbers of 12 mm dia bars at both the ends. So if we are providing boundary element, the minimum longitudinal steel should be at least 4 numbers of 12 mm dia bars. So that is also checked because we are using 6 numbers of 16 mm dia bars. Now let us try to check or assess the safety of the tension element. We have the tension element, which is the another boundary element at the other end. In that case, the gravity load will still be compressive in nature. What shall be the gravity load in this case? 0.1 times of 0.8 times of 2500 divided by 1.5. Why did we do such a calculation? Because we have seen it in the last class that when assessing the safety of tension element, we will consider the gravity load to be 0.8 times the design axial force. So this one we have calculated it as 133.3 kilonewton. Now due to external moment, what would be the tension? So the remaining moment which was being carried out by the boundary elements in tandem, one in compression, one in tension, so divided by the lever arm gives us the value of tension force in the tension element, and therefore the total force in the tension element becomes equal to 133.3 kilonewton minus 420.4 kilonewton, which is minus 287 kilonewton, which means this element has a tension force of 287 kilonewton. Now how will you find out the tension carrying capacity of the column? Since concrete is very big in tension, we will not consider the concrete contribution in tension. We will only consider the contribution from the steel reinforcement. Assuming minimum steel requirement, that is 0.8% of steel, that is 1200 millimeter square, in the boundary element having cross section of 300 mm by 500 mm. So if we assume this minimum steel, then the tension carrying capacity shall be 0.87 times of 500 megapascal into 1200 mm square, which we can calculate and find out to be 522 kilonewton. Since this is larger than the tensile force in the tension element, this is suitable. Now, for providing this minimum 0.8% of steel, that is 1200 millimeter square of steel, we can provide 6 numbers of 16 mm dia bars with 3 on each face. Now, this provided steel, as we have calculated it earlier, is sufficient. Further, let us check the other ductile detailing requirements for this steel, that is the maximum diameter of vertical bars should be 1/10 of wall thickness, which means the diameter of vertical bar cannot exceed 1/10 of the wall thickness, which means 300 divided by 10, 30 millimeters. We have used 16 mm dia bars, perfectly fine. It is also larger than the minimum longitudinal steel if the boundary element was not provided, that it is more than 4 numbers of 12 mm dia bars. So, what we have found out that both the boundary elements, the compression element and the tension element, are safe. Now, let us design the transverse reinforcement in the boundary element. So far we have designed the longitudinal steel in case of the boundary element. Now we are designing the transverse reinforcement. How we will design? We have studied in the last class that we need to provide a special confining reinforcement throughout the height of the boundary element. What shall be the area of the steel? It is given as ASH equals 0.05 SV times of H divided by FCK upon Fy. Now we will assume two-legged 8 mm dia closed tie and one 8 mm dia cross tie. Why are we using a cross tie in addition to a closed tie? Because the boundary element is 300 mm by 500 mm. So if we only use a closed tie, there are greater chances or even surety that the distance between the parallel legs of the transverse reinforcement, that this closed tie, will be more than 300 millimeters, which is not suitable from ductile detailing perspective, that we have looked into when we were designing columns. So therefore we will also provide one cross tie. So effectively you can say that we are using 3-legged 8 mm dia ties, and in that case the value of ASH can be calculated to be 151 millimeter square, from which we can calculate the value of SV, that is the spacing between the transverse reinforcement, at 143.6 millimeters. Now for ductile detailing requirements, there are few criteria for checking the spacing. The spacing should not exceed 1/3 of the minimum member dimension of the boundary element. The minimum member dimension of the boundary element is 300 millimeters, because it was 300 mm by 500 mm. So 1/3 of that minimum member dimension is 100 millimeters. Then the spacing also cannot be larger than 6 times the diameter of the smallest longitudinal bar, and the longitudinal bar which we have used is 16 mm dia. So it is 6 into 16 or the 96 millimeter. Then 100 mm, we cannot exceed the spacing by 100 mm, but it may get relaxed to 150 millimeter if the maximum distance between cross ties of parallel legs of the links is limited to 200 millimeters. Then since in this case we have the distance between cross tie of parallel legs of the link lesser than 200 millimeters, as it may be clear from the geometry or from this assumption. So this can be relaxed to 150 millimeters, but based on all these criteria the lowest is 96 millimeters. So you cannot have the spacing more than 96 millimeters. Therefore we are providing 2-legged 8 mm dia closed tie and one 8 mm dia cross tie at 90 millimeters center to center spacing throughout the height of the boundary element. Now at the start of the problem we have identified the requirement of the boundary element based on the axial force or stress in the extreme compression fiber, which was exceeding 0.2 FCK. But at some height the axial force will keep on reducing, and at some height it will be less than that. But at that point you do not have to truncate the boundary element. You can truncate the boundary element when the axial stress in the extreme compression fiber is less than 0.15 FCK. Alright, so we have designed and detailed the horizontal and vertical reinforcement. We have also designed the boundary element. Now let us look into the reinforcement detailing of this special shear wall. As you can see that we have provided a mesh of horizontal and vertical reinforcement bars in two curtains. You can see over here, and horizontal and vertical bars both are 10 mm dia bars at 200 mm center to center spacing. One thing you should also be noticing that the horizontal bar is located outside the vertical bars for a good confinement. So that is a good side practice that you should be observing. Then in the boundary element, in this boundary element and in this very boundary element, you can find that the longitudinal reinforcement comprises of 16 mm dia bars. There are 6 in numbers in this boundary element and 6 in number in this boundary element, and the stirrups or ties in the boundary element comprise of 3-legged 8 mm dia bars at 90 mm center to center, which comprises of 2-legged closed tie and 1 cross tie. It is shown over here. It is self-explanatory. Also it is shown in the elevation as well. This brings us to the end of today's class as well as this week. So far we have completed discussing the seismic design and ductile detailing of reinforced concrete buildings. In the coming week we will take our journey forward to seismic design and ductile detailing of steel buildings. Thank you.